Welcome everybody to Argonne OutLoud. This is the laboratory's public lecture series. Talks that highlight the best of what we do here at Argonne in science and engineering, as well as other topics that are of interest to the community at large. My name is Al Saddleberger. I'm one of the associate laboratory directors here at the laboratory. I'm responsible for the applied science and technology piece of Argonne National Laboratory. And it's my distinct pleasure this evening to introduce tonight's speaker, Don Hillebrand, who's listed on the slide up there. And at the end, we're going to raffle off some rides on the Back to the Future car that's pictured there. Yeah. But before I introduce Don, I'm supposed to remind everybody that you can access the laboratory's website and download videos of the previous Argonne OutLoud lectures, read about our science and engineering that we do at the laboratory, and sign up for our monthly email newsletter. So Don is the director of our Energy Systems Division here at Argonne. He is responsible for an organization that conducts applied research to develop sustainable technologies that are directed at improving the efficiency of both resources and energy use, minimizing our dependence on foreign energy, and enhancing our national security. It's a big job, and he does a great job at it. Previously, he was director of Argonne's Center for Transportation Research. There he directed a team of engineers and physicists, and maybe a few chemists too, Don? Okay, I hope so. Working to solve transportation problems related to our dependence on imported energy. Don came to Argonne from Daimler Chrysler AG in Stuttgart, Germany, where he worked as the manager of research and technology policy in the company's research labs. He spent 2 years in the White House Office of Science and Technology Policy as the senior policy advisor for transportation, so he knows a lot about the subject. Previously, Don spent 20 years as a product engineer with Chrysler Motors. Don is currently the president of the Society of Automotive Engineers, or SAE International. He's been a member of that organization since he was 18 years old. He tried to get in earlier, but they had an age cap. He's received many honors and awards and was named by Automotive News recently as one of the 100 most influential people bringing about the electrification of the automobile. Please join me in welcoming Don as he speaks about the future of transportation.
All right, well, thank you and welcome. It's really a pleasure to have you here. Welcome to Argonne National Lab. It's such a fine day. I know what kind of sacrifice you're making coming here. It's the first warm day we've had in a long time, so I really appreciate it. Before I start, I want to thank members of my staff who came here as well. They've been the people in the back who have been working the posters, working the cars out front. It's a real sacrifice they make, and I want to let them know I really appreciate it. That's a great sacrifice to make, and it's very helpful, and we'll remember it when performance appraisal comes. Why is this one of the scariest days of my life? It's because not only am I talking about something I've spent 30 years working on, but my 3 teenage daughters are in the audience. That's scary. There's nothing I can do to be successful. I can break even, and I'm gonna try very hard just to break even today. That'll be the best I'm hoping for. We have an interesting topic from my perspective. I run the transportation group and the energy systems group, which is a very exciting part of the lab. We're a little out of step in some ways with what a national lab does. Traditionally, national labs do basic science and big physics and big science type projects, but we're more of an applied group. But that's what makes it interesting, and that's why we've actually been focusing on objectives and tasks that are things that happen immediately, things that are happening in the near term, things that really impact society right now. The transportation group is one of the fastest growing. It's one of the youngest groups at the lab, and we really grew out of the stresses and strains of society over the last 10 or 20 years. We're about that old when it comes to the work we're doing. Our objective is to reduce our nation's reliance on petroleum consumption, and at the same time to reduce the environmental impacts that vehicles will make on the world. That covers a broad range of different types of technologies. And one of the exciting things about my job is we get to touch all different types of technologies that are affecting transportation right now. And our job isn't specifically to be cheerleaders for those technologies. It might surprise some people in the audience. We're not up here, I'm not up here, to talk about how wonderful the technologies are. It's quite the opposite. Our job is to find the faults with these technologies. What's wrong? What are the shortcomings? What are the weak spots? What are the weak links? And at what points do these technologies break down? Because ultimately they have to stand the strains, they have to stand the fire of competing with existing technologies, and we want to make sure that they're ready to go and go forward. So what you hear from me today might be a lot of essentially negative talk on a lot of the different technologies. What are the problems? What are the things we're trying to overcome? Why are we actually working on these things, and why are they here? That's something that we focus on. In a lot of ways, it's difficult to be the person who explains why technologies don't really have a great potential, but in a lot of ways, it's a lot of fun too. All right, so what I'm going to talk about the future of transportation, and as I was thinking about this, I thought I should have some sort of a metric, some way that we compare what we're working on with what expectations are, to try to understand, are we really meeting the types of expectations that people had? So I thought, how do you do that? How do you really see if you're developing things for the future the way you hope to? And I came up with a thought that you want to compare it to really what predictions have been made in the past. One of the best predictions I could think of was the movie Back to the Future. Back to the Future was a movie that was made, it came out the year I graduated from college, and it was essentially about a young man who goes 30 years back in time, and he's just overwhelmed with how much society was backwards 30 years before. And then in the sequel, he goes 30 years into the future, and he's overwhelmed by how far things have advanced. And there are a lot of other things that come into the movie, but it struck me as I was sitting thinking about it. He went 30 years into the future. He went to 2015. He went to next year. So I've got that movie. I have it on video cassette. And so I can actually look at the movie. And so I took the movie and I broke it down because a lot of the technology breakthroughs they're talking about were related to transportation. So I grabbed 11 predictions made in that movie. And as we go through this talk and I talk about some of the work that we're doing here at Argonne, I want you to think about some of those things because we're going to do a wrap-up at the end and see how well we did on a range of 11 different types of technologies that I saw in that movie that may be significant. So the 11 technologies would be flying cars, something called Mr. Fusion, which was sort of a small, pocket-sized, unlimited amount of energy, food hydrators, self-adjusting, self-drying jackets, phone glasses, something called the US Mail Fax Service, holographic movie theaters, remote hovering news cameras, the Scenery Channel, something called rejuvenation centers, and then finally the 11th that I picked out of that movie was something that seemed at the time absolutely truly impossible by 2015. And we're going to see it right at the end whether or not we were able to meet that objective as well. Now, so keep that in mind as we go through this. All right, give a little background, a little context about energy use and transportation. Our society has been shaped by how it uses energy. Really, from the creation of man, how we've been able to access energy and use it has really shaped what we are. And as we've made different discoveries and moved forward, it's really changed fundamentally how far we could move, and it's changed how society was adjusted from that. Over in the upper corner here is a model of what Ötzi looked like. That was the Iceman who was found under the glaciers in Austria-Italian border a couple of years ago, 20 or so years ago. And he's the oldest complete man we have. He's about 5,500 years old. And he had with him a little energy storage container in his pocket when he was found. He was limited by the energy that was available to him. The amount of food he could put into his stomach was really about how far he could go, but he was found far up in the mountains. Why? It was because he had a little birch container in his pocket wrapped with maple leaves where he kept hot embers and coals, so he could carry his energy with him. It was like a little battery he carried, which extended his range from that little village he probably lived in at the base of that glacier all the way up to the mountaintop where he was able to go. So it was that ability to keep and store energy and use energy that allowed him to go beyond one day's walk away from where he was actually living. As we begin to develop different energy sources, that diameter of where we can go has changed, transportation was adjusted accordingly, and our society has changed as well, from the ability to carry more massive energy sources, burning wood. The horse and buggy, of course, expanded how much we could carry, how much food we could bring along. It was energy storage that allowed us to have a bigger and bigger diameter that we could go, until finally we discovered a small black rock that was a very concentrated source of energy that we could light off and use to release lots and lots of concentrated power, and that was coal. We discovered coal when we were nearly running out of wood, and really coal was just discovered to keep you warm. The ramifications of that were far more than anybody expected, and that is when they discovered coal, and how concentrated that energy was and that we could release it, it really spawned the industrial age. Steam engines came directly out of that. From that came trains, steamships, deep mines, a lot of industrial processes in the entire Industrial Revolution, which changed fundamentally the world, the way we looked at it, because we had a new concentrated form of energy. The next step was gasoline. Gasoline is a byproduct of kerosene. They were making kerosene to make lamps. Gasoline is a product that you have to throw away when you're trying to make kerosene, and it was considered a dangerous explosive substance. But somebody had the idea that this extremely concentrated form of energy, that is gasoline, could be used as a power source. Ultimately, the internal combustion engine came out of that, and the internal combustion engine has changed society drastically. It's given us personal transportation, it let us come out of cities, it let us ultimately develop light enough and powerful enough power that we could get into the air, that we could develop aircraft, faster aircraft, and from that directly came passenger aircraft, then jets, and really, as a final point, we developed rockets that let us break the bounds of Earth and go into space. All of that came from developing more and more concentrated forms of energy. Now, we don't know what the next form of energy is going to be. We thought we were going to go into a nuclear age, and we have to some extent, but it hasn't really, there aren't nuclear airplanes yet. They worked on some. They didn't really get off the ground. But the next step of energy is something that's open to debate right now, and very likely it's going to be electricity. It's probably going to be the electron. And the question will be, how do we actually hold that electron, and how do we use it for transportation going into the future? We've had electricity for a long time, but it's been limited by how long the cord is. We're now finally getting to the point where we can hold those electrons without having a cord take us to some place. We're developing battery chemistries and battery technologies that allow us to concentrate so much power into a small area that we might feasibly be able to use the electron as a source of transportation. What's going to happen? I don't know, you know. The consequences of that could be very negative, could be very positive, but a very small, powerful amount of electricity in your pocket that could allow you to go a long ways, or lots of places, could fundamentally change society as we know it. I don't know what it's going to look like. It's probably not something I'm going to solve. The younger people here, maybe my teenage daughters, they might be the ones who are actually going to solve that problem, but it'll be something that goes beyond what I'll be working on. Transportation has spawned not only advances in society, but a lot of problems. That's why we're here. That's why this lab was built. It was to deal with the problems that have come out of the transportation byproducts, negative byproducts. Three main things we've worked on over the last 10 years. Really, people have viewed as the biggest problems we have to deal with when it comes to transportation. Smog and toxins, climate change, and energy security. Those were the mantra of our three objectives, was to try to deal with each one of those. And for 10 years now, we've focused on it. And I think we've really focused on it with some success. If you look at the smog and toxins aspect, it's really viewed, and this is arguable, somebody out there will certainly disagree with me, as not an issue anymore when it comes to vehicle emissions. If you look at this chart, it's a two-dimensional chart of particulate matter and NOx, or nitrous oxide, the emissions that come out of internal combustion engines. In 1970, this entire sheet would have been representative of how much came out of the exhaust pipe of a car. That's when you think of Los Angeles as a kind of a brown, hazy area, and Chicago as a brown, hazy area, and all the pollution that we had. Steadily, we developed technologies, many of which came out of national labs, the catalyst, advanced catalyst, particulate filters, projects that we've been focused on for a long time that allowed us to crank the standards down to 1985, 1988, 95, 98, 2002, 6, 10, till ultimately 2014 we're going to have standards that are that big. Where we're going to go after that is into the future. The European and American standard should take us to about a point right there. That's how much we've changed fundamentally from that to a single point. So is it still a problem? It is. But it's a true fact that the emissions from the exhaust pipe of a 2013 automobile in Chicago on a summer day are cleaner than the air that goes into the engine. So in some places, Chicago being one of them, the air's dirty enough that cars clean the air. So that's where I'm going to say problem solved. We'll have continued pressure in other areas. And you may ask, why is the sky still brown? That's somebody else's problem. That's not my problem. Energy security is one of the other issues we've focused on, and we've begun to see real success in energy security area as well. This has been a big issue for a very long time. It's really directed our policy decisions over the last 20 years, maybe even longer than that. The access to cheap oil, to petroleum, protecting our energy supplies are fundamentally important to our economy, and in many ways, they've been one of the things that we've spent a great deal of our treasure on. Three impacts of oil dependence are wealth transfer from oil consumers, us, to oil producers, loss of economic output, and the dislocations caused by the oil price shocks, the hammering that our economies taken when prices go up and down and up and down. Those have been three very real costs. For 2008 alone, the three economic costs for foreign oil dependence are estimated to be almost $560 billion, one-time cost, flowing out of our country and into other countries. Over the last 5 years, over a 5-year period, not the last 5 years, that cost was estimated to be $1.7 trillion that flows out of our pockets and into other people's pockets, money that we could have. So that's been a real problem, and we've been focused on that relentlessly in our group, in my lab, and a lot of labs for a very long time to try to take care of that, and I can say we've had some success. U.S. oil production has been increasing steadily since 2005. The drop stopped in 5. We leveled out for a while, and we've started to increase. We've leveled out for a lot of reasons. The red chart is the U.S. oil production, and as you can see, it bottomed, and it is spiking, and this is a good curve. If this kind of curve continues, we'll be net oil exporters in a very short time. I don't think it'll stay on that course, but I think we're picking low-hanging fruit. Some of the new technology has spawned. The blue line is Central and South America, which has been relatively steady, which shows that it's not just technology everywhere. It's really what the U.S. has been focusing on. As such, this chart shows our oil dependency, which has been steadily dropping. Here's our import levels that went up to as much as 13 million barrels a day, and they're now dropping, I think it's around 6 million barrels a day right now. Down here in 2013, it's down around that level. That's a real success. Now that's positive, but it's also because of some bad things too. Part of the reason for this drop is our economy really had some difficult times back in 2008, and that dropped some things down. But the other reasons are efficiency has picked up fairly substantially, and probably the biggest factor is new technologies developed in the US have allowed us to find substantially more petroleum within our own borders. Now, so problem solved? No, it's not. Part of the issue we have is that price volatility remains. The sawtooth that you see here is a substantial swing in price of oil just over the last couple of years. And that's a real problem. When oil goes from 140 to 40, back up to 120, back down to 80, you're in a situation where nobody can make any sort of plans. You know, this is a bigger question than just what we have to put into our car. This is a broad question on the economy, and it's very difficult to make decisions as investors, as economists, as policy leaders, when that's the kind of price swing that we're seeing. And mark my words, as we're finding more oil, the price is still staying up, and it's going to probably stay up into the future. Side note of interest is that natural gas has gone down and is projected to stay down for a very long time. Now, why is it whipsawing up and down? What are the problems? The problem is it's no longer inside our country where all the consumption is. It's moved outside of our country. We're stable. We're now quickly finding enough energy to use ourselves, but other areas are the areas that will grow. The blue bar is the 2030 growth in different countries. And if you look at Asia, their growth is expected between now and 2030 to almost double. We're going to grow a little bit. Europe's going to shrink. And some other economies are going to show fairly substantial growth, although they're smaller to begin with. But that Asian growth alone is phenomenal, and it scares investors. It scares analysts. It scares a lot of people, and that's why the prices are whipsawing, and probably why the price hasn't dropped down to the point where we want it to drop to. Even if we did find enough oil within our own country, remember, while it's illegal now, I think, to export oil outside the US, very quickly, that amount of wealth will find a way to go to other places. I'm pretty sure that we'll find a way to figure out how to export that oil. So why are we focused on it? Why is the government concerned about it? For the reasons I just stated. So our transportation research program is focused on the National Energy Resource Goals. And that goal could be stated really one thing, and that's dramatically reduce or even end our dependence on foreign oil. It's coming, but the technologies still aren't in place to make it happen, and we're not sure that it's reliably going to be something that goes away. Let me give you a short commercial for Argonne National Lab. Half of you here probably work for the lab, probably work for me actually, since you're here doing the posters, which I appreciate. But Argonne National Lab is one of the 17 major national labs. Our challenge is to do world-class fundamental science and engineering, providing solutions to national challenges. And my national challenge, of course, is the transportation and energy question. The 17 labs are located, as you see. We lump Argonne and Fermi together because we're managed by the same group and we like each other so much. We kind of consider ourselves cohabitating in some way. But the labs all have different specific missions in one way or another. Argonne is one of the full-service labs, and that is we do pretty much everything. If there's a science that needs to be developed, biology, chemistry, physics, computation, we do it. But many of the labs are specific and have just narrow targets. Ames Laboratory works on rare earths and materials, fairly small lab. In Denver, the National Renewable Energy Lab focuses on wind turbines, renewable fuels, and solar technologies, that sort of a thing. Down here in the corner, we have Lawrence Livermore and Sandia and Los Alamos, weapons labs. You know, they're focused on a lot of weapons projects. They're very big labs because of that, but that's really their specific target. Savannah River does nuclear type storage. Idaho National Lab works on nuclear energy. Oak Ridge National Lab, we cooperate with them, we like them. They're our closest ally, our closest competitor, and they're very much like our lab. In the lab transportation program, as I said, it's probably between 10 and 15% of the lab based on how you want to measure it. I would prefer to measure it as about 20% of the lab. I think other people would probably look at it as about 10%. But it's all a matter of what circle you want to draw around transportation. But we really have the lead role in several areas, which I'm going to talk about now. We're the lead lab for hybrid vehicle systems, including plug-in hybrid electric vehicles, modeling, benchmarking, and evaluation, and component integration. We do engines emissions research, in-cylinder combustion. We work on biofuels. We're working right now on natural gas, a very exciting and growing area. Batteries, battery chemistry, battery processing, battery manufacturing, fuel cells, vehicle recycling. We're looking at replacements for rare earth materials, which are the exotic materials that are in new batteries and that are in new electronics. We do applied materials research, tribology, which is the science of friction and wear. We're working on nanofluids and nanoparticles to lower the need for lubrication. We have a very big push on high-performance computing. And finally, we have analysis and assessments. And the analysis and assessments is a really interesting area because that's kind of the decision-making that goes into all the different directions that the policy wants to go in. I'll start with analysis and assessments. I run a group that's called the Life Cycle Analysis. Now, you see many different ideas for different types of technologies. And it's a very difficult thing to face all these technologies, try to understand what they can do, and try to evaluate them and compare them with each other. A technology that in one hand looks like it's brilliant, when you actually step back and step back again and see the whole picture, you realize, no, there are huge problems. There are huge costs associated with this technology that looked just right here like it was such a good idea. Life cycle analysis is about looking at the whole tail, the head, all the guts that come out of it, the sawdust from the wood. It's looking at all the waste, not just the finished product you're going to see. Ethanol is an interesting example of, we look at ethanol and we say, oh, it's a great fuel, it's made from corn, it's perfectly clean. But you step back and say, well, when you grew ethanol, what were you going to grow there instead? You grew something that was probably food-based. Okay, where did that go? Well, that went to the Amazon where we cleared this huge basin and displaced people and did all sorts of damage. And you say, oh, okay, well, we need to put numbers on all those things. So the job of this group is really to look at all the different technologies and put real numbers or real metrics on how they function. For instance, some of the things we'll look at as leading candidates for doing good things for us for transportation. Conventional spark ignition vehicle engines, direct injection engines, diesel engines, fuel cells, battery-powered vehicles, electric vehicles are the rage right now. Hybrid electric vehicles, plug-in hybrid electric vehicles, how do they all compare? What are the big problems with them? Looking at the entire tail and trying to understand it is a big part of what we're trying to do. But, just realized I have a clicker here. When you really break it down, you have to understand these technologies and compare them in a fair way with each other. One of the ways we do this is figure out how would you measure it. Well, there are two good measurements. The first is dollars, and the other one is carbon. Carbon is kind of a measure of efficiency. You know, the amount of carbon that's produced in doing something can be looked at the amount of waste that goes into it at the same time. And you could extend that to what kind of damage you're doing to the world. You can look at it in a lot of different ways. But it's a very good metric for comparing things. And dollars are somewhat nebulous. So what we do is we try to compare them using grams of CO2 per mile per technology. And we have a wide range of technologies that we try to compare. Here's 2012 gasoline. All the way over here at 430 grams per CO2 is where our vehicles are for transportation right now per mile. That's how much carbon we put out. So all the new technologies we're talking about, we try to compare to that number. Well, the first thing you want to do is know, well, where's gasoline really going to go? Because everything's improving. And that's 430 is the average of where we are now. Where's it really going to go in the future when all these other technologies? So we can run that and determine it's going to be sort of a range here from about 170 all the way up to maybe as much as 300. We're guessing it's going to be about 220. That's where gasoline's going to go. That's the bogey. That's what we have to compare to. Now let's look at other technologies. Diesel fuel. Bit of an, wait, I'm sorry, 220. Diesel fuel, bit of an advantage. Natural gas. Again, we slide over a little bit. But when you look at these comparisons, they have to be not only good enough to beat gasoline, you've got to then take into account, well, what do they cost? What are the impacts? What are, other things that come into play? Is it really worth going there just for this minor increase. And that's the analysis that has to be made from that point on. So look at corn ethanol takes us down a bit. Cellulosic ethanol, which is essentially ethanol made from agricultural waste, takes us down. All these technologies, we can almost draw a line here. If they cross the line, we probably aren't interested in looking too deeply at them. What's interesting is the amount of uncertainty you'll see in some technologies. Like this long band here is a battery electric vehicle with a 100-mile range. Battery electric vehicle with a 300-mile range. Why such a big uncertainty? It's not so much because of the technology as much as it is the world makes its electricity in a lot of different ways. And our country makes its electricity in a lot of different ways. And if it's very clean and at the base of Cooley Dam, you're probably here. And if it's in the northeast United States, it's probably up here. So you have to understand the whole amount of technology, the whole range that you've got. And this is really the chart we use to try to shuck off and throw off different technologies. A few things jump out, These down here that are renewable energy, of course. If you make it from a battery electric vehicle that runs off a complete renewable, you end up with very little carbon emitted. But then that's where you have to step forward and look at some of the costs that come into play too. And you may find that the costs and other inconsistencies have spiked. But that's the way we do the comparison. Argonne's got a broad range of responsibilities. Some of the technologies that we're focused on, or some of the capabilities we're focused on, is finding out how you compare different types of technologies and also how you compare different types of vehicles. One of the main benchmark groups that we have, it is our benchmarking group, is the Argonne Advanced Powertrain Research Facility. Their job is to take every new interesting technology that comes out on the road from a vehicle standpoint and figure out how it works. Reverse engineer it. Take it apart. Break it. Figure out how to rebuild it. Learn everything you can about it. Learn how its control system works. Learn all the tricks that are in it. And basically take it and flip it over and figure out how we could actually do it ourselves. Here's a chassis dynamometer, which is essentially a giant treadmill for a car. It has a beautiful Tesla on it, which was a very challenging car for us to test because we got no cooperation. We had to basically break everything to get into it. But it's this type of a vehicle that we're doing testing on to determine energy consumption, emissions, performance, vehicle operation, and strategy. And our objective is, for the US government, determine how the best vehicles from around the world function and feed that, for lack of a better word, feed that to American companies and to the US government. A lot of nations do it. That's what our job is. Our job is to reverse engineer technologies, develop control systems, and help American companies compete and do a better job. Here's a list of some of the vehicles that we've actually tested. I mentioned the Tesla, the Mini E. We build our own prototypes that we test, the Nissan Leaf. We did a whole lot of crazy vehicles for X Prize. Only we had the capability to test them when it came forward. Battery electric vehicles, plug-in hybrid electric vehicles, biofuel-driven direct injection vehicles, and even fuel cell vehicles. We've covered the whole range. This is just a snapshot. We have a whole database of different types of technologies, and really our job is to take all these things, break them down, figure out how they work, and compare them with each other. Now, there are three major technical areas that I really want to talk about. We have a lot of projects. I'm going to offend a whole bunch of researchers because I can't talk about everything we have. So I thought I'd pick a couple of the leading candidates and some things that are of interest right now and talk about why we're working on them, shortcomings we see, and where we think it's going to go. Electric vehicles, combustion vehicles, natural gas vehicles, a wide range of different types of technologies. First, let's talk about electrics. EV Everywhere is the initiative put forward by the Obama administration in March of 2012, and its focus is to enable the US to be the first in the world to produce plug-in electric vehicles that are affordable, convenient, and literally as good as gasoline-powered vehicles within the next 10 years. Very ambitious goal. It's got a long way to go. They're putting a lot of resources behind it. It involves developing a lot of different aspects of technology, and much of that work has come to Argonne for us to work on it. Now, electric vehicles are nothing new. The first vehicles were really electric because it was the easy way to do it. Electric vehicles at one point were a majority over steam vehicles and gasoline vehicles. So they really held sway for a while because they had the nice power-to-weight ratios. They had a lot of advantages. But ultimately, they died. They were taken out the first time through by different technologies. Now, they made a revival in 1995 where General Motors built what's considered to be one of the best electric vehicles of all time, the EV1. And once again, a movie was made about that one dying as well. Again, it didn't make it. It died for lack of public interest. It died for cost. It died maybe because it was killed by its own parents, they say. It's hard to say. There have been a lot of ideas as to why it went down, but it did go down, so it failed twice. So we're trying it again. Why should we expect it to be any different? What's different now? Well, technology is moving forward. The things that have killed electric vehicles have been fairly uniform. Range has always been the thing that killed a vehicle. The electric vehicle suffers from the fact that when you leave the driveway, you've only got 100 miles of range, maybe, and that scares a lot of people. The costs have been considerable, so costs have been an issue. They use a lot of rare materials, rare earth materials that I mentioned earlier, that are available only in very obscure parts of the country, which limits how many we can make. And finally, there's a question of infrastructure on how to charge them. That's not free. People say, oh yeah, just plug it into my garage. That's very true for you. But once 2 vehicles or 3 vehicles or 4 vehicles go on the same transformer, that transformer is no longer capable of lasting the 50 years it was designed for. In fact, if you do thermal cycling for vehicles that were built to go that far, you quickly end up with a 6-month transformer. And from 50 years to 6 months is fairly dramatic. So it's something that has to be considered and has to be understood, how the grid can handle all those types of technologies. Now range, we've heard some good announcements of range. It sounds like it shouldn't really be a problem, but it turns out that range is something that's very much variable, unlike a gasoline vehicle. Factors that affect it. We did a test recently on a Nissan Leaf, and we just wanted to see what would the effects of high temperature and low temperature be on the range of a vehicle. Let's grab just the urban drive cycle and see how it really affected it. The urban drive cycle indicated we have a certain energy consumption, in this case around 200 DC watt-hours per mile, which gets you about a 100-mile range of the car, a little less than that, about 80-mile range. However, in cold weather, you have to turn on a heater, and all the electrics and battery hate to be cold. Your range, your consumption doubles, which means your range is cut in half. So what was a 80-mile car is now a 40-mile car. So we just went from me getting to the O'Hare to not making it to O'Hare and back, which is a big concern. In the heat, it's the same thing. If we have a 95-degree day, I have a 30% increase in my consumption. Once again, my range, which was 80, drops down to 60-some points, and it's not really what I expected. And remember, I don't want to just drive and just get in the driveway and run out of fuel. I really want a little bit of cushion, especially if my 3 teenage daughters are in the car with me. All right, so how are we doing? How are sales looking so far? EV Everywhere has just started to get off the ground. It started to make a push. They're focused on how we get lower cost materials. A big push on that, a big aspect of that is going to be battery development at Argonne National Lab. We're looking at grid development, trying to expand our grid and make it smart and make it more intelligent. So a lot of things have to come together to make that happen, but there are just a lot of obstacles in place, and it's not going to be a simple thing. Let's look at sales right now for the electric vehicles. These are all the electric vehicles, plug-in vehicles that are available on the road right now. As you can see, the sales are steady, but they're not what people hoped for. Nissan, which is the hash mark at the bottom here, the Nissan Leaf, had projected their sales to be at 10,000 by last year. As you can see, they're not even, at this point, they're around a tenth of that, and not very consistent. So they're very, very far behind what they hoped to meet. Now, the other big vehicle in here is the Volt. The Volt's an excellent vehicle. The Volt doesn't have range issues. The Volt uses plug-in technology to take care of a lot of the concerns of an electric vehicle, but even with those advantages and a good price position, it's still only selling a couple thousand a month at best. It's close to their target, but we're not going to really make that big impact on our infrastructure if we don't sell more vehicles than that. Tesla is the bright red here. It's hard to say. Tesla's made a big splash. The question is, are they really going to sell? They've had some bad months and some good months. It's an expensive car. I guess the next few months will tell us whether it'll take off. But at this point, $60,000 for a 4-seater is a very expensive car. It is probably worth it, but there aren't that many people who can afford to spend that kind of money on cars. The other aspect of it is how we make the grid work. We're focused on working on grid technology. This is one of the things that Argonne has got responsibility for. It's called vehicle-to-grid interoperability. That is making sure that the car talks to the charger, talks to the links, talks to the power providers, talks to the stations, that everything is interactive, that everything links together, because at this stage it's not the case. The grid in the US doesn't even talk to itself, let alone, I think recently we brought some German vehicles in to charge them up in the United States, and it turned out that the German vehicles made by a major manufacturer, I think it was, they were Opels, no, I'm sorry, they were Audis, would not charge in the US. They had to bring in generators, and they had German generators on trailers following the electric vehicles around so they could charge them up. That's the kind of thing that we're focused on, and ultimately the real efficiency is going to come from figuring out how all these things talk to each other and making them talk very efficiently, because there's a lot of waste in the system, and really our objective is to try to take care of that waste. Energy storage. Everybody will tell you when it comes to electric vehicles, it's the battery stupid. However you emphasize that. It's the battery. The battery is the thing that makes a difference. The cost of that battery, and also its power density, its safety, its efficiency. All those things have to roll together to really make it work out. Now, just announced here, and I think it's going to be a topic that's talked about in the future, so I won't go into it, was a project called Caesar. It's a 5-year program to develop the next generation battery, and they're going to do it right here at Argonne. The battery in the Volt, which is probably the most advanced vehicle in the world right now, is an Argonne product. That was developed in our labs. It was partially scaled, and then it was licensed and partnered with LG Chem, and so that commercial product on the road right now, the best battery in the world, came out of Argonne chemistry. Probably the next generation is going to come from our labs as well. And going into the future, Caesar is focused on a 5-year project to get, 5/5 the cost, 5 times the power density, all the 5s, which is really going to be some exotic chemistries that are going to take us off into the future. When you look at the range, I forgot that I actually had this here. When you look at the ERE goals, it's taking 300 cells, a $10,000 battery, and getting it down to where it's only 100 cells. It's literally a $3,000, even smaller battery, using some of the new exotic chemistries beyond just lithium ion to lithium sulfur to lithium air or to just pure lithium. Really interesting where you can take it. Right now, it's just something that's happening in the lab, but ultimately, they'll expect us to make the breakthroughs and make the inventions that'll take that battery to that point. When I talked about taking a battery to actually make it where we could have a battery economy beyond gasoline, that's what's going to do it, that kind of work. So how are we doing? Well, in March, the president came here to see where all the batteries in cars are being invented. The president came specifically to our labs, to many of the researchers in this room, and walked through and spent an entire day looking at our chemistry, our facilities, our vehicles, our engines, and talking to the researchers to get an idea as to how it's going. I looked at this as an extreme honor. When he looked for a place to come to point out well-spent federal funding, making big advances, he came to our lab. Let's talk about engine research briefly. Now, electrics are one area, but there's a horse race going on. What's nice about Argonne is we're kind of betting on all the horses. In fact, we kind of own all the horses, so we know we're going to win. But engine research is one of the other leading candidates that's going forward. The engine, that horrible, idiotic internal combustion engine, just keeps getting better. And everything that competes with it ends up getting beat by it because there's still so many more places we can go. Argonne's engine research really spans the gamut. We go from automotive all the way to locomotives. We look at a whole range of different types of technologies. We have state-of-the-art engine facilities. We have a diverse skill set. We get funded by a whole bunch of different areas, from Department of Energy, from industry, from government agencies. We have a wide and very interesting staff focused on some really cutting-edge technology. When you look at the internal combustion engine, if you looked at this whole circle as 100% of the energy that comes in the gasoline, when it goes out, 62% of that energy just goes away as heat. It's just throwing out the exhaust pipe or keeping my wife warm on the other side of the car. It does probably both of those things. In terms of engine mechanical losses, 16% of it is lost to overcoming friction, accessories, pumping work. 10% of it is drivetrain mechanical losses, transmission, differential, bearings, and seals. And only about 12% of it actually gets to the point where it's moving the car forward and gets you to where you want to go. So all this is waste. And everything we're doing in the internal combustion engine is figuring out ways to take that waste stuff and turn it into transportation, cutting down on the losses. And there's still a long way to go. We're just scratching the surface with engines. They're really exciting now. As I said, they're clean. Once they're clean, you can start to play with a lot of other things you couldn't before. Variable valve technology, cylinder deactivation, direct injection, going from 2 strokes to 4 strokes, diesels, dual clutch technology, flywheels, electric hybrids, intelligent transportation systems. There's still a long way to go. There are a lot of breakthroughs that are still going to happen. One exciting project right now is an engine I like to call the CIT Engine. Steve CIT is around here someplace. He's working on an engine right now that is essentially a diesel engine, but the diesel engine burns gasoline instead of diesel. Why? Well, the advantage of a diesel is it's very efficient. It gets everything you can out of the expansion of those burning gases. The advantage to gasoline is it's very clean. We know how to clean it up completely. So if we can take a diesel cycle, if we can burn gasoline fuel in it, we have clean, we have efficient, we've got 30% more efficiency, possibly, of fuel economy. That's going to make it really hard for the electric vehicle to take that extra step. Because remember, when you're buying that electric vehicle, you're thinking, it's going to be, let's see, 7 years before this is paid off. Okay, makes sense. Now, if the gasoline vehicle is 30% more efficient, it goes from 7 years to, that's 12 years. And yeah, I'm not even going to have hair in 12 years, so I'm not really sure I want to invest in that vehicle at this point. It makes it that much harder to really go to that point. Some of the projects we're working on, we're taking big physics tools and looking at how combustion works. It's a project by Dr. Chris Powell. It's using the building we're in right now. Yeah, we're in the advanced photon source, I'm sorry. Using the advanced photon source, the brightest light source in the hemisphere, or at least the brightest one in Chicago, and using it to actually look at fuel and combustion and understand better how fuel injection works, how combustion works, how to make it cleaner, how to make it better. In the past, all we knew was this is a vapor cloud. What's happening in the vapor cloud? No one knows. You can't look inside it. But with these tools, we can look inside. We can see where the concentrations are. We can see what's happening. We can look through things. We can look through steel. We can look inside combustion. We can look inside flames. It's a new way of actually completely understanding projects, completely understanding combustion and having a better feel for how the whole thing goes together. From that, we've been able to get more and more efficiency. Supertruck Program. This is a project by Dr. Andrew Ikes and Dr. Thomas Wallner. They're focused on taking a vehicle and getting a 50% improvement in fuel efficiency. It's a partnership we have right now with Navistar, taking a heavy-duty truck engine, which currently gets about 5.5 miles per gallon, taking it up to 9 miles per gallon. Doesn't sound like a lot. That's a phenomenal increase in efficiency because they burn so much fuel. All our freight is hauled that way, and you're looking at substantially better usage of fuel. So that's another project we have going, which is very interesting. And then we also have a tribology group. I think we have some people talking about our tribology work as well. Advanced lubrication, focusing on identifying pathways to improve fuel efficiency. I talked about all that was lost through friction and wear. Well, we're looking at lubricants and additives, we're looking at materials and coatings, and we're looking at engineered surfaces, all of which allow you to have very hard, low friction, non-wear surfaces that take the friction out of an engine, that keep attacking all those different aspects of it. That's why the internal combustion engine is going to continue to improve, and that's why we're going to continue to go and have a real race between different technologies. Who's the third horse in the race right now? Natural gas. Everybody, have you all heard about fracking? All right, fracking is the method by which we drill down into rock, we horizontally drill, we fill it with high-pressure hydraulic fluid, crack the rocks all around, put in some sort of grit substance that holds the cracks open, and then we can collect natural gas. It's a process that's been invented over the last 10 or 15 years. It's a multi-administration, multi-agency effort, and it's come to fruition. We're expecting our natural gas resources to triple from 2009 to 2035. We're finding massive quantities of it. This is a growth curve based just on seven shale basins. There are many more shale basins in the US. And internationally, it looks like there are a lot of places we're going to be looking for natural gas and probably finding it. So natural gas is going to be a reality. New technologies, they have gigantic energy and environmental implications. Now, are there problems with it? The holes are dug, so that gas is coming out. So really our objective is to figure out how are we going to use the natural gas that we now have. There are a lot of concerns, there are a lot of questions that are going to be made, but the natural gas is a reality right now. We have to figure out what we're going to do with it, because ultimately, with that kind of resource, we may ultimately become an energy exporter, not only with gasoline, but with natural gas as well. So the big push right now is to figure out, what do we do with this new natural gas? I mean, there is no infrastructure for it. As of 2011, there are 885 compressed natural gas stations and 44 liquid natural gas stations in the country. And only half of those are actually public, so you can't even use them. So those dots represent where all the stations are. That's not enough to really build an infrastructure. We've got the gas, and there are a lot of uses for it. The first thing we're going to do is, heat homes, produce electricity, make fertilizer, all the other things you do with natural gas, but we're still presuming we're going to have a lot left over, and that's really the question. What are we going to do with it? If you took all heavy-duty freight traffic in the country and charted it, bigger the traffic, the more traffic, the thicker the line, the country would look something like this. So one of the objectives is to try to take all the freight traffic we have and build selective and creative natural gas stations so that we can at least first transfer our heavy-duty transport from diesel fuel to natural gas. So that's an interesting way to go. It's something that could actually happen. And it looks like we can do it with only several hundred natural gas stations. But there are still problems with natural gas even beyond that. For instance, how do you fuel? How are you going to use the natural gas? 2 ways to put natural gas in a vehicle right now. And by the way, it's clean, it's efficient, great aspects of natural gas. It's great to run it through an engine. 2 ways to use it. One is compressed natural gas. So what are the problems with compressed natural gas? When you compress it, you're wasting a lot of energy, just doing the compression. When you store it on a vehicle, even if you compress it to 10,000 pounds per square inch, you still need a massive tank to hold that much, which isn't a lot of range. So your range is going to be greatly diminished, and truckers like range. Next, it's just the physics of fueling. Go to PV equals nRT. When you pack all that gas into a chamber, it heats up. So you can't get as much into it as you need to. So you got to wait for it to cool off before you can put more in. So fueling, which used to take 5 minutes or 10 minutes, it's now 20 minutes or 40 minutes. And truckers don't like to sit around. They like to get home. So that's going to be a problem that we have to solve. How do you solve it? Well, a whole lot more stations, which is a whole lot more cost, which causes issues and problems. The other way to handle it is LNG, which is liquefied natural gas. That's nice because it's liquefied. You can just dump it into the tank and go, and it's really clean and easy to use. The problem is to liquefy natural gas, you have to spend a massive amount of energy to liquefy it. And then you've got to spend energy on cryogenics to keep it liquefied. So you've now thrown away, some estimates are as much as a third of the value of the natural gas just to get it into the car. Suddenly you're throwing a lot of value away. Suddenly when you start to compare it to diesel fuel, it's got issues. One of the proposals we're going to take to Washington next week will be an idea for using the existing natural gas infrastructure to get to transportation. How are we going to do it? Well, 50% of homes in North America have natural gas piped right to the door. It's a small pipe, it's not high capacity, but it's there. So if we could tap into that, this is the idea we have, if we can tap into that in each of those 50% of homes and have a vehicle that is biofuel, we could possibly displace a lot of petroleum. How do we do it? Well, biofuel is really easy. An engine doesn't care if it's running on gasoline or natural gas. It's pretty easy to make it switch back and forth between them. The problem's always been how big is the tank and how do we fill that tank up? So the idea we're going to pitch to the Department of Energy next week is, how about a small tank? About a gasoline, 1 gallon equivalent gasoline. How about that big a tank, and not much bigger, maybe 2 gallons? That would be maybe 50, 60 miles just in that little tank. The tank can be inexpensive. It doesn't have to be high pressure. And the first 50 miles you drive every day, it can fuel itself all night long. Natural gas that comes to your door, which by the way is about $1 a gallon equivalent, would allow you to displace most of the driving you do with natural gas. The average person drives 27 miles a day. So if you had twice that size, you would really take a huge whack out of our petroleum usage. Wouldn't affect infrastructure. You could probably make a real impact. The idea is you start with that kind of a tank, small CNG tank, but you also can run on gasoline if you run out of natural gas, so it's not an issue. Slowly we get bigger CNG tanks as we develop and solve the problems with materials in the tanks, smaller gas, and ultimately we can get to the point where maybe we have built out an infrastructure, but it's done over 20 years, not over a couple of years, and we're actually If I had a natural gas laptop, and if I have to pedal something, I'm just not going to do it. So. Are we okay? So you can keep working on it, and I'll just go quicker. So let's talk about the future right now. So those are some of the projects we have going, and you get an idea, the feel for the kinds of work that we're actually doing. What are the problems we're going to face in the future? They're going to be a little bit different. The main problems you start seeing coming along, we still have an energy issue. We're going to deal with congestion. We're going to deal with safety. We're going to deal with competitiveness, national competitiveness. Congestion is a serious issue. The world's problems, congestion, as the Asian economies grow, is going to be a very serious thing we're dealing with. And the way we're managing that is going to be changing fundamentally what a car looks like. These are some renderings of vehicles that may allow the new urbanized future to have transportation. Smaller cars, not really what we think of as vehicles. Easily stackable, easily parking, very efficient. By 2020, 60% of the world's population will probably live in megacities. They'll control 80% of the wealth, but only 14% of the population has access to personal transportation. The rest aspire to personal transportation, or many people aspire to personal transportation. So that's one of the concepts we're going to go forward. But the most exciting one you're seeing right now is automated driving. We've talked about this technology has existed for a long time. I worked for Daimler in Europe for 4 years. We had automated vehicles. We linked with it, we called it the electronic tow bar. Vehicles in long links can platoon with each other, go at very high efficiency, and travel at any speed they want because while they don't touch each other, they're completely connected. When one brake is hit, all the brakes hit. It acts as one giant vehicle, and vehicles can peel off and come back in. Why did we build it? terrified our lawyers. And I don't blame them. Here's the problem. As you see some of the things, there are all sorts of fuel economy advantages we can get from robotic driving. It's not a very complex issue. Google's been doing it for the last couple of years. It's really getting easier and easier to do. We've done it for a long time. The problem is there will be accidents. They're unavoidable. Now, we're working on an accident-free car. Maybe we'll get to that at some point, but there will be accidents because it just happens. And when that happens, there are going to be lawsuits, and the big auto companies are terrified of those lawsuits because they know what it means. That's why the smaller companies like Google have been willing to take it on because, frankly, their exposure is a lot different. If they're modifying somebody else's car and it crashes, then that's all confused right now. Nobody's really sure how we're going to solve that problem. But one thing that's true, and that is the future, to get rid of our problems with congestion and other things, we're going to have to go to fully automated. Vehicles that all talk to each other, vehicles that know where each other are, vehicles that can keep us from getting into accidents, vehicles that can take over when you're too tired, vehicles that maybe can drive all the time. That's really the point we could potentially go to. There's a whole range of things. It could drive better efficiency. It can help us avoid accidents. At the same time, it's going to result in a loss of driving autonomy. There are huge concerns about lawsuits related to the accidents. It opens us wide open for terrorism, security problems, threats, loss of privacy. And the other issue with many of the people that I worked with in the auto industry is all of them viewed as something that was going to be just tremendously boring. Why are you in the auto industry? Because you love driving. So are you going to work at a car that drives for you? That was a hard lift. Google can do it, but I think the Corvette team is probably not going to be interested in working on that. So another future thing to take care of congestion, how about flying cars? This is something that worked very well in the movie. If you look closely, I think you can see the cable there by how they hung it. Are we going to go forward on flying cars? Actually, yeah. I go to Oshkosh every year. Oh, by the way, yeah, I looked up flying cars. The first one I saw was a Pinto from back in the 1970s. Can you imagine a more scary thing than a Pinto that flies? You can see like the gasoline trailing out of it as it flies across the... But at the same time, flying cars are becoming a reality. There's a company called Terrafugia, forgive me if I'm not pronouncing that right, it's making a really serious effort. Are they going to succeed? Nah, I mean, we see companies like this come and go. Maybe they will. They've got an interesting product. It's at Oshkosh every year. They're hypothesizing actually making a very advanced sort of flying aircraft. It's really exciting if you could potentially do it. Do I personally feel that's going to happen in my lifetime? No. We can't even handle vehicles on the ground hitting each other. When you put them in the air, it gets very scary. Although if you think back, Henry Ford's first objective after doing the Model T was to build something he called the Flivver, which was personal flying transportation for everybody. There was an accident. One of his favorite subordinates was killed in the accident, and he decided, no, I'm not working on airplanes ever again. But think if he'd actually gone forward. He was building a small aircraft that everyone could have. Now at Argonne, we're working on electric aircraft, just with some of the companies, Sikorsky and some of the other companies that are interested in it. And we think that maybe there are some aircraft applications, but this is quite far out. I don't know if we'll ever get there, but I wanted to just say it's something that people talk about. And every year at Oshkosh, there's a little bit better driving aircraft that's out there. They have all kinds of problems. Not so much from the air side, but from the ground side. So, and the other aspect of it is, from flying aircraft, just thinking about that. If you know Elon Musk, inventor of Tesla, PayPal, SpaceX, I got to spend a couple hours with him a few weeks ago, and he's going to go to Mars. He's building rockets, and he's going to go to Mars. He's going to send 80,000 people to Mars. That's his objective. And while it sounds silly to begin with, when you see his factory and you talk to him, he might do it. He might be able to do it. He's building that many rockets. He's currently feeding equipment up to the space station. He took a 100-foot tall rocket case, full-size rocket case. He can take off, fly, and land, take off, fly, and land with carbon fiber landing gear. It's amazing. I went there, and I was truly inspired. And at 50 years old, I don't get inspired by many things anymore. But he's actually going to do it. And if you think about flying cars, on Mars, a 180-pound man would only weigh about 60 pounds. It's just physics. So it doesn't take quite as much to fly a car down there that it does here. So maybe flying cars will first happen on Mars. All right, in conclusion, the US is blessed with adequate energy supplies. We really, when you look at other parts of the world, we have an amazing amount of energy. Solar, wind, biomass, coal, nuclear, tar sands, shale oil. We're finding our new natural gas resources. If you took all the oil in the world and put it into a pot it's about 40 cubic miles of oil. If you took all the natural gas, you're looking at from 300 to 500 cubic miles of the equivalent same sort of energy. Massive more amounts of oil. If you look at coal, you have literally 1,000, maybe 1,200 cubic miles of the same thing. So oil will be gone soon, may or may not be. We have so much more energy, and a lot of it's right here in North America. Our challenge isn't to find the energy. Our challenge is to figure out ways that we can use that energy, supply us for mobility. So the end game, the 1,000-year vision, is wind, solar, or nuclear energy, adding water and coal and electricity, all things we have in North America, and turning it into synthetic fuels, into power, and into transportation. But beware of Jevons Paradox. For everything we're talking about, Jevons Paradox comes in more and more to play. Jevons Paradox, the proposition that technological process that increases resource use efficiency inevitably tends to increase the rate of consumption of that resource. So the more oil we find here in North America, the more we're going to use and the more we're going to waste. A good example of it is, why do we live in the desert? It's because of air conditioning. So we live in the desert because we could, and we're throwing away massive quantities of this resource because we no longer need to live in logical, sensible buildings in the desert. Now we can have big glass boxes that need massive amounts of air conditioning. So we figured out how to cool ourselves, so now we can waste the technology. All right, I'll wrap up now. I'm sorry for going so long. The 11 predictions for Back to the Future. Let's start with flying cars. We're going to make it by next year? Nah. Going to make it in my lifetime? I should live so long. We're not going to get to that point, so from the transportation side, we have failed you. I'm very sorry. Mr. Fusion. This is Mr. Fusion back here. It's a little coffee. Oh, here it is. I'm sorry. Little coffee maker. It's supposed to produce fusion. If you look at the equivalent right now, it's probably Mr. Fission. And Mr. Fission is about the size of a tank truck. And it's a small mobile reactor that's being worked on here at Argonne. It doesn't run on banana peels and beer. And it's got a long way to go. Are we going to make it by next year with Mr. Fusion? No, we're not going to be even close. Food hydrators? No, I don't even know any research going on food hydrators. We're failing you. My generation has failed so many people. Self-adjusting, self-drying jackets? Under Armour. It's close. Mine seems to dry itself pretty well. Phone glasses? You guys see the Google glasses just came out? That's one. We did it for you. US Mail fax service? That's email. All right? Remember, in '85, we didn't know what email was. That's two we got for you. Holographic movie theaters? Anybody see Avatar? Did you stay awake through it all? Well, I'm going to take that one. Remote hovering news cameras? Look at the news these days. There's a camera everywhere, okay? So we've done that one. It's 4. Scenery channel? We call that the internet. Or Facebook. And then finally, rejuvenation centers. I've never been to Hollywood, but I understand that they've actually been able to accomplish that. So we're not doing too bad. We probably got 6 out of 10, but I would say 7 out of 10. But I would say the first 3 are probably, or the first 2 are probably the really important ones, and we haven't made as much progress on those as we should. What was the 11th one? What is the impossible thing that was predicted by that movie? Does anybody remember? Way to go, Cubbies! And it's not going to happen, so. However, all things are possible to him who believes. And I believe. So thank you for your attention. I'd be happy to take your questions.
Okay, questions from the audience? Start right here.
I got a piece of low-hanging fruit for you. In '87, I left Germany, and we had sequenced traffic lights. You spent 4 years in Stuttgart.
Fella, yeah.
I bet you I'm going to go down Ogden tonight, and guess what? None of the lights are sequenced. Nowhere in this country, I think, have I seen sequenced traffic lights.
Okay, my turn. So you mentioned that in Germany, they do sequenced traffic lights, so when you go down strips of long streets, if you go exactly the speed limit, you can make every light and just fly through. Grüne Quelle. But what I noticed was the locals found that if you went twice as fast, you could still hit them all. You're not saving energy if that, so No, that's just, I'm sorry, I had to push back on that. You're right, it's a very interesting thing. We don't do a good job of traffic control. We have a group called TRACK that's working on traffic control and the impacts in the Chicago area of modeling traffic. I think we need to do a better job of it. But I think that's an aspect of intelligent transportation systems, that there is still a lot of waste in our system, and we could find so much of that waste if we start to do things more efficiently and better. And going twice the speed, maybe that's the efficient way to do it, I don't know. Anybody, any other? Yes, sir.
Yes. One technology that I don't think I saw you mentioned, and I'm curious as to where it is in the mix, are fuel cells.
Yes. Fuel cells, you know, technologies, they come and they go in different times, and there was a major push in 2000 to 2009 on fuel cells. Big progress was made. Fuel cell projects, fuel cell vehicles really accomplished from the vehicle side almost all of their goals. But it was the well-to-wheel analysis aspect of it that's really been part of the holdup. Auto companies have built fuel cell vehicles that solved just about every problem they had. You know, the transients, spraying water on the road, cold weather, efficiency, they solved every problem down the line. The issues they've been dealing with are fuel supply. The hydrogen, to make a fuel cell work, you had to build the infrastructure and put the fuel cell and put the hydrogen on the road. The problem we dealt with is that was a long-term commitment that had to go over the last 10 or 15 years. Hydrogen stations have had to been built over the last 15 years, and literally none have been built. So there were a lot of reasons for it. I won't even get into why they're not there, but what holds fuel cells up is the fact that nobody's actually spent the money to build those stations. They haven't given up. The Europeans announced recently, I was in Germany a couple of months ago, or actually, I'm sorry, last August, BMW is making another big push on fuel cell technology. Honda, Toyota, General Motors, they all built really first-rate vehicles, but they're still waiting for the fuel to come along. And that's a question that I think still requires some fairly major technical breakthroughs before we're going to get there. Nobody's given up, though. That's still a fairly solid funded program. And we have work at Argonne that's along the lines of trying to solve those problems. Yes, sir.
Dr. Hillebrand, I've been doing a lot of reading on compressed air engines.
Oh, yeah.
And I think there's a lot of pros for that technology, but I haven't seen too many cons. So what are the cons?
Like the Scuderi engine? Is that what you're talking about? The Scuderi,
I'm sorry?
The Scuderi air engine?
Yeah, there's also one in India, there's one in New Zealand, a radial one.
Yeah, you know, we looked, I had a slide in here, I had so much stuff I wanted to talk about. That was actually about some of the six-stroke engines, some of the exotic engines, Scuderi engine, a range of different types of engines like that we're focused on. They've gotten commercial interest. Companies have actually picked up some of that technology. I've looked at it. There are some shortcomings with the designs in terms of sealing and in terms of manufacturability. But at this point, while some of those companies have come to us and asked us to evaluate some of their technologies, I think they have potential. The hard thing for those new engines is that they really have to compete against very established engines that are super, super cheap. Some of those new technologies require a lot of new components that make it difficult for them to compete. So it's going to take a lot of investment, and they simply haven't been able to line up the people who want to come run and put the money into it to make it happen. I don't see a lot of fundamental breakthroughs that we need to do, that it would come to a national lab, but I do see products that people are interested in. Really, their step is to bypass us completely and interest the industries and the suppliers right now directly, and that's something they're having trouble with. I think we have a couple of engine researchers here who could probably talk to you specifically about what the shortcomings of those engines are, but we've looked at them and we're interested in them. At this point, no one pays me to work on them, so I can't work on them.
Yeah. Over here.
Oh,
yeah. Another technology that seemed to be coming along a few years ago was this high-pressure compressed air. I thought the company Tatra in India had bought that technology, and then it seems to have just fallen off the face of the earth. I'm curious what happened to that, if anything.
We're hesitant to talk about a specific company or technology because I have to be very careful whenever I try to bring up something like that, because although we're a national lab, we still can be sued if we badmouth a technology in one way or the other. It's interesting to me that it hasn't really taken off, and I'm not sure why. We haven't been asked to do an analysis of it. There was a lot of spin from the Tata technology, and I think it's just dealing with the teething problems and shortcomings of actually taking a technology from something that works great in the lab one time to actually taking it into a vehicle and taking it out into the world. That's the the thing that just kills so many very promising technologies, that when you actually get to the point where you say, all right, this works, we're going to commercialize it, you've only gotten through 10% of the issue. Now you've got to do the real engineering, and you've got to do the process, you've got to do all those types of things. I don't honestly know the answer to your question, but I'm presuming they're hung up in that portion of it, and that is there are just a lot of unforeseen problems. As they say, 10% of the problem is actually 90% of the problem. And I think they're probably in that phase right now. Okay.
Don, you mentioned that in several places, technologies that will change the fuel requirement from the current gasoline-diesel mix. What effect will that have on the U.S. refining system?
That's a good question. You know, the question is, you know, as we go more to diesel, where are we going to get that diesel from? Because right now, all the refineries in the U.S. crack their oil, they split it into gasoline and diesel. I'm very much simplifying this. You take your diesel and you put it in a freighter and you send it to Europe. They do the same thing, and they take their gasoline and they put it in a freighter and they take it to the U.S., and we're very happy about that. So what happens if we begin to use more and more diesel technology? It's a good question. The price could go up. There's certain flexibility. Petroleum engineers tell me that there's flexibility in terms of getting more quantities of what they want out of it. There's also an interesting aspect of natural gas could be turned into a good diesel fuel too if you want to. So that's a way we could augment some of our diesel aspects, is taking natural gas, converting it and mixing it and blending it with the diesel that we have. Or we might just decide that the part we crack, we want to keep, because at this point the new oil that's being found is being found here in North America. So I don't know how they're going to go forward on that. That's an interesting question, and we're all kind of sitting back and looking at it. Our analysts, I'm sure, are considering it, but at this point it's not been one of our major things we're looking at.
Question over on that side.
Are you looking at the social aspects of car usability, like, for example, car sharing, like zip cars and things like that? Because I know you can get a lot of utilization out of electric vehicles that way.
That's a really good question, and I thought about getting into that area, but I didn't want to talk too much about it. The social aspects of cars, I mean, how often does your car actually run? For the most part, your car is a very expensive, and in my case, a beautiful piece of equipment that sits and doesn't do anything almost all the time. I mean, how often are you driving? You're only driving 5%, 3%, something like that of the day. The other 97% of the time, it's a very expensive and valuable asset that sits unused. So there are a lot of different concepts that come into place as to how we could actually maximize the use of that. Car sharing, zip cars, excellent approach, and it's slowly and steadily growing, and that is a car that you just, when you need a car, you get a car. Pick it, you drop it off when you're done, and you know, you leave it for the next person. There are issues with that. I know we tried doing that with our bikes here on site, and inevitably all the bikes get clustered in one area, and then we have to go haul them and take them all over the place because everybody seems to want to go to the same place and then walk back. So there are those issues that you deal with. Oh yeah, and in Washington, D.C., they had a bike sharing program, but they found that all of the bikes ended up at the lowest spot in the city over and over and over again. That's not really the problem with zip cars, but I think there's a lot more efficiency we can get out of vehicles. First of all, just through using a zip car type approach, where some people who don't care about their car other than I need to get from here to there, it works perfectly for. Some people love cars and enjoy driving, and for those people, I think you're always going to have a market for those type of people. But for many people, they say as many as 40 to 50% of people, a car is just a thing that gets you from this place to that place, and I don't want to deal with anything else. Those people are prime candidates for car sharing, for zip cars. You know, maybe there's some social tools somebody will eventually put together that will allow us to crack the issues of insurance, security, and all those types of things. Those are social issues. We're not working on them. People are working on them, and I think they're fascinating because the whole aspect of how we use cars is something that's not, to this point, really not that well understood.
This question comes via Twitter. Daniel Yunt in Oklahoma wants to know what new materials will play a big part in the future of planes, trains, and autos, and he also asks what new energy will also change the game.
What new materials are going to take...
What new materials will play a big part in the future of planes, trains, and autos?
Sure. I mean, one of the big pushes right now from the Department of Energy, and they're coming out with different challenges now at a steady rate, looking for new types of materials that are going to be important to us. One of the first ones was, let's get rid of cast iron. You know, cast iron. We're still using cast iron in so many parts of a car, and it's just simply come up with something that can replace cast iron. So we're looking at different types of aluminums, different types of copper alloys, different types of steel alloys that can replace just plain old cast iron. When you look at trucks and when you look at trains, that could actually have a fairly big impact. So from the standpoint of that. Second, everybody heard about the BMW i3? A fascinating car. It's an all-electric vehicle with a carbon fiber frame. Somebody finally decided just to say, you know, we're just going to build it out of carbon fiber. I know it's expensive. I know all these different issues. But when you're done, you've got this stinking light car that's just fast and strong and efficient. And ultimately, when you do some analysis on it, it may turn out that you can use that frame a whole lot longer than the car is going to last. So you might have recycled frames. And BMW decided, I think they're going to build about 4,000. I got to tour their plant. They wouldn't say how many they were making, but you kind of count up how many tools there are. You count up how long everything is. You can kind of figure that probably 4,000 vehicles they're going to make per year. And they're just going to do it. It's going to be expensive, but it's really interesting because I'm excited to see what carbon fiber could mean. For a long time, the government's focused on trying to get the cost of carbon fiber down, and they really haven't had a lot of progress. It still costs about as much per pound as it ever did, and they need to come up with a good process to get that price down, but that'll be something I think that'll make a major change. Other materials that are going to be interesting, we're focused right now on something called wide bandgap materials. That's the replacement for silicon and for semiconductors. It's a very exciting thing that will probably make power electronics a whole lot more efficient. Argonne's part of that. We're competing with all the other national labs right now, and we're actually cooperating with the other national labs to try to be part of that. So that's an area that's going to have some interest. So structural materials, as I said, carbon fiber, cast iron replacement. Electronic materials is going to be fairly interesting. And then, of course, ultimately, the material that's going to be extremely important in the electrified future will be what that new battery material looks like. And I think that's going to be something that's specifically going to be invented here at Argonne. I'm sorry, the second? Are we good? Okay.
Yes, I mentioned fuel cells with hydrogen. I was under the impression you can also run fuel cells off of methane. Is that true? And if so, couldn't you just use the CNG with the fuel cells?
You can. That's one of the approaches, is to run fuel cells directly off other types of fuels, but you have to reform it and turn it into hydrogen. So what you're doing is you're either running the fuel cell, you're either making your hydrogen here at the station, concentrating it, putting it in the car, or I'm taking that whole factory and I'm making a tiny processor that'll do the same thing and putting it on the car. But I can't at this point. It's a chemical process, and at this point, it needs hydrogen, combines with the oxygen, we get water, we get power. So it's hard to short circuit that. You still have to do something when you're dealing with say, natural gas. You still got to do something with the carbon. It's got to go somewhere. And so it just makes it a much more complex system. They've had some success trying to do that, but ultimately, and that's one of the things Argonne's working on, is reformer technology that can take different types of fuels and turn it into hydrogen and carbon dioxide. But at this stage, they haven't really had something that can solve that problem yet. They're working on it.
We touched on the hydrogen cars because I thought about 6 years ago that was decided that that was going to be the way of the future. Some announcements were made. On the automated cars, what would be different from having mass transportation instead of each person or a couple of people sitting in one car and being driven around? You're in a mass transportation mode.
So what's the difference between just an electric train taking me from one place to another as opposed to automated transportation system? When I lived in Washington, D.C., I worked in the White House, and I took public transportation, which was fabulous. It was about a 20-minute walk to where the train was. It was about a 10-minute run, then it was another 15-minute walk after that. It was about an hour for me to take public transportation to get from where I was to my office in the old executive office building. When I drove myself, it was about 10 minutes. So that's the difference when it comes to an automated system will let me get in the car. It knows where the traffic is, it knows where everything is, and it can get me right where I need to go immediately. So I think it's really a time question when it comes to public transportation. I'm not anti-public transportation. I think it's a fabulous option. I think we should be building that out. There are a lot of things that we should do with respect to public transportation, it's such a useful thing to have because it enables so many other technologies. So it may make it difficult for the U.S. to compete, but ultimately it's difficult to compare the two because one is just so much quicker than the other.
Thank you for the great talk. And I'm glad you mentioned time because I just finished reading a work by Ivan Illich, Energy and Equity, written 40 years ago. And he makes an interesting case that he said at that time we have not moved forward much in transportation because when you add the time driving the car and the time that you spend on traffic, stuck in traffic, the time you spend working to pay for the car, for the gas, for the highways, then he estimated that the average driver drives 7,500 miles, and it takes 1,600 hours to do all that.
Okay.
So when you calculate the speed, then we're really not moving that fast in cars. Now, that's a 40-year-old work, so I was wondering if, since you initially talked about how we shape society, the way we move and the way we use energy, if something along those lines of the social aspect that we're talking about could have a place on the work here. Thank you.
I mean, we're all pretty good about understanding about how much time we spend on things. I think everybody, you kind of know where you're wasting time and where you're not wasting time. But it's a good point. There are a lot of things that probably go into driving that we don't even consider as we're getting ready to do it. It's got to be considered.
You had a bullet point regarding the battery swaps, and that could be potentially a good solution to the charge time issues for BEVs. So, but recently there's this company, Better Place, which didn't do that well. So, could you talk about some hurdles with the battery swap technology?
Well, that's one of the issues near and dear to my heart. The question is battery swapping. For a long time, there have been companies that have been touting a technology by which very simply, you take a battery. When your cars run out of juice, you take the battery out, you plug another battery in, and you continue on. It's a simple idea. A lot of venture capital and investment money was pulled together to put together the idea. I won't mention company names because we're not supposed to do that, but I did read that a major company in this field just went bankrupt yesterday. And for a very long time, they've talked about this as a technology. It's a simple idea. Ultimately, I think we'll get to that place. But the reason we're not there now is the economics of the whole situation have to be considered in a broad way. When you're going to have a big battery pack, what's the major cost in an electric car? It's the battery. So if I'm going to have spare batteries, I might as well have spare cars because there's so much cost in the extra batteries. So if I've got half the value of the car in a battery, and I'm going to keep a spare battery there, I'm sorry, I can't afford to do that. So that's a very difficult thing to have lots of extra batteries around. The other issues are things like we have to have the same battery for all cars, which we don't have yet. We don't even have the same chemistry for all cars, let alone the same battery. So until we get to a common battery, we get a huge number of vehicles on the road so it can make sense. So the utilization efficiency of the vehicles goes up. When we get to the point that the batteries are super cheap, at this point, a battery costs maybe $10,000 or $15,000. They're warranted for 3 years, 4 years. That means I've got to get my investment back. I've got to make a return on investment. I've got that battery pack. I've got to make 4% at least if I'm going to invest in it. And I've got to pay off the battery. So over 4 years, I've got to make $3,000 or $4,000 per year on that battery pack that I've invested in that sits on a shelf someplace. Now, what's the value of the electricity that's in that battery pack? It's $2. So it's $2 a day if I'm using it at its absolute max. That's like $600 of energy that I can possibly put through that battery per year. And the battery costs $4,000. How am I ever going to get my money back? So there are a lot of things that people needed to step back and look at battery swapping and think about the big picture. It's a great idea. It's too early. We haven't developed to the point. We don't have enough vehicles out there yet. We don't have cheap enough batteries. And we really needed to step back and think about it. And I was kind of surprised at how many people were willing to invest in that technology because it seems straightforward just from a finance standpoint. I'm an engineer, so I don't do finances very well. But still, you would think somebody would step back and say, oh, right, you can never make your money on that. Nonetheless, I think we have to wait until there's a much bigger inventory on the road. And then I think it's got a future. I mean, look at the AA batteries. Think of a big AA battery, and they're all over the place, and they're really low cost. That'll be the solution someday. We have to wait. We have to wait for society to catch up with our technology.
Two more questions.
Two more questions.
One over there, and then the last one over here.
Who might?
Okay.
The gentleman up here talked about production of new engines, new types of engines. And you talked about some of that too when you talk about carbon footprint. Advent of 3D printing. How do you think that's going to change the transportation?
3D printing is fascinating. I think in 2 dimensions. I'm a 1980s guy. I'm sure one of my kids is here. Maybe they could handle it for me. But that's a good question. I don't know. I really don't know. I think it's going to be an exciting thing. It's one of those tools, you know, like when they invented the laser, they said, wow, this is cool. What do we do with it? I don't know. But then after a period of time, it's like, well, we can do optical reading, we can play music, we can shoot things out of the sky, you know, on and on. I think it's the same way with 3D printing. We're going to need a lot of very clever minds who are in universities right now using 3D printers to focus on the different things that can happen. And we need to advance the technology. And I think it's a very exciting thing. I have no idea. That's a good question. I'd like to see some fairly simple papers written on it, so I might get some information. Last question.
Okay, so I noticed this is a seminar about the future of transportation, yet I noticed you are pretty much talking about cars. What about the other methods?
I'm sorry, cars for?
This seminar's titled name is The Future of Transportation, yet you're talking mostly about cars. What about the other methods of transportation?
Yeah. When we lay out and look at transportation, and try to compare different types of transportation, the biggest piece of waste of all the transportation is cars. It's personal cars. That's why we focus on that area. When you look at a train, what kind of fuel economy does a train get? Does anybody know? 400 ton miles per gallon. 400 ton miles per gallon. What's a truck get? A heavy-duty truck on the road. Gets 25 ton miles per gallon. So yeah, good answer. What's a Toyota Prius with a person in it get? 4 ton miles per gallon. Because remember, the only freight is that person. Nothing else. The weight of the car doesn't matter. It's moving a person. So it's hideous fuel economy. That's worse than a 747. So why are we talking about cars? It's a good point. There are many things we can talk on. And we have projects in locomotives, heavy-duty trucks, small vehicles. We're looking at some advanced type vehicles. But cars are really where the waste is. Cars are the thing we need to focus on because that's where fuel is wasted. That's where inefficiency happens. And that's where there's the most room for improvement. So we're going to focus on those areas. That's where most of our projects are going to be. And we know that looking at those areas first will make the biggest impact on the world. So thank you very much for your time, and I appreciate your questions.
Thank you, Don.